Okay, let's continue. Wait, just want to check that, yeah, okay. And now what we will do is to finish this one. Also note that by using this result, and note that by, is this the one? Just put some bound over there. Now, look, if you look at the condition on eta, there it's easy to see that since eta is the step size is in less than 2 times the norm of a to the minus 2, then it's easy to see that the norm of a squared is less than 2. Okay, and also t is, as you can see, when we take the supremum, t is from 2 to the norm of a squared. So that means that if you combine these two here, then you can actually see that eta times t is less than or equal to 2. And this also follows that if you have minus 2 is less than or equal to minus eta t. So that means, how do I say it again? Also eta t is, of course, not negative. So that also implies that minus 1 is less than or equal to 1 minus eta t. Okay. And then this is also from this one, you'd add 1 here, add 1, then that's equal to 1. So that means that 1 minus eta t is less than 1. That means that, of course this is true for all t from 0 to norm of a squared. And this tells us that we have some bounds on g sub n of t. So that means if you remember the bound for g sub n of t, that means it's bounded above by this one. So every term here in the sum is less than or equal to 1. So there are n terms there. So that's less than or equal to n. And also that's 0 over here. And g sub n of t times t from this expression here, this is bounded above by taking absolute values there. So this will be equal to this. This one will be bounded above by 2. So that's bounded above by 2 over square root, 2 over just eta. Okay? Okay, so just take the triangle inequality here, something like that. Okay? But you don't need we don't actually need to take the absolute value here because this is not negative anyway. So this is less than or equal to 2 over square root of eta. Note that's eta. I have to make it distinct from n. And then, as a consequence, we have the following result, which is what we will need later here. Okay? So that means if you have g sub n of t times square root of t, square root of t, because notice we have a square root of t over here. Okay? So, of course, we can rewrite this one as in that way. No need to, it's safe to take the square roots here because g sub n's are non-negative anyway. So times t. We put t here. And then using the two previous results, this is equal to square root of eta times square root of 2 over something. Sorry, I think I messed up with my notation. Sorry, guys. This is n. Okay, but it should be n. Why did I use confusing notation? So that's equal to 2 times n over square root of eta, rather square root of 2n over eta. So therefore, we can now have the final estimate here. Finally, useful error bound here. So that means x sub n delta, x sub n is less than equal to, so that's eta times this one times norm of y delta minus y. And simplify that one, you will get that one over there, that's square root of 2 times n times eta times the norm of y delta minus y. And that actually gives the first estimate, because we can write this one as in our desired form. So using the condition of y delta minus y, this is equal to, by isolating the terms without n, so that's square root of 2 eta times n to the 1/2 times delta. And this is C1, okay? Okay? There, okay? So that's for the first estimate. For the second estimate, it also follows the same procedure as what we used last time, but we will use the error decomposition that we used here, actually. So let me bring that one out, down. Okay. Okay, so from here, okay, and from here, we lift the last result that we have, something like that one over there. Let me just, now I'll use the analog with the A star outside, okay? So actually here. So we use this one again, okay? So just imagine if we multiply it by A on both sides here, okay? Okay. So therefore, from that one, we can see that A times xn delta minus xn minus y delta plus y is equal to this one, eta times I times A star times that sum over there, A times A star okay, and then times y delta minus y. and then minus, I'll just group it in this way. Okay, and then now if you look at this sum over here, we can how do I say that? We can actually transform it on a more useful estimate by looking at this term over here. Let's write that as n times AA star as equal to I minus eta AA star. Okay. So what we'll have is something like this. Maybe I'll put a bracket here, times the summation here. Okay, and then you have this one. And then by distributing the sum here to here, so we'll get something like this one. So since we multiplied by the identity, we can just write the sum right away. Minus, note this summation, this term here, can be safely multiplied inside by spectral calculus. So you can just simply write it as summation of I minus eta AA star to the j plus 1. And then you have y delta minus y over here. And now by simplifying the first term here, notice by subtracting these two sums, some terms will be left, and what will be left here is this, because this one starts from, no, it starts from j equals 0, so that's equal to 1, okay? And then, yeah, and then from that one, you will, by simplifying that 1 over there, actually we can do it in a more detail. Oh, actually, I should have just, yeah, that's fine. We can write this one as I, and then plus j equals 0, plus some summation of from j equals 1 to n minus 1 of the same term there, and then minus the same term here. And the terms here from, let's say, from j equals 0 to n minus 2 of the same term here raised to j plus 1. So that's j. Okay. So, and then subtract the last term at, I'll just make this one as something like that. Okay. To the, then minus the term at j equals n minus 1, so that's this same term here raised to n. Okay. Okay, and then if you look at this one, these two summations here will be cancelled, right? Oh, this is n, that's n minus 2, because we're isolating the term for j equals n minus 1. So what's left here is this one, so this gets cancelled, okay? And then we are left with the following, which is actually that one. So that's I minus this term over here raised to n. Okay. That's AA star, sorry. I minus AA star raised to n and then you subtract it by minus y delta minus y. Simplify that further, you will get a simpler result, which is actually that one, which is, because this gets cancelled here. Okay, and then you'll get something like this. Okay. So for that one, we get a very useful result over here. And then by that one, we can take the norm on both sides. Then we will get that one over there, which can be directly obtained. So let's finish it. Oops. Okay, there, and then from that one, you will get something like hello. So that will be equal to, take the norm on both sides, up there. The norm of I minus eta AA star raised to n times the norm of y delta minus y. And again, we can use spectral calculus here because f of, actually the same f as what we used, actually no, if we let f of t be equal to 1 minus eta times t, then we have f of AA star equals the identity minus eta, actually there should be n. And from spectral calculus, spectral calculus, we can show that f of A times A star is less than equal the supremum of absolute value of f. In this case, that's equal to the supremum of 1 minus eta t raised to n, and t is taken from 0 to norm of A square. And from the previous computation that we have, this is less than equal to 1, which means that this is less than equal to 1. By applying this one here, this is less than equal to 1, so this is less than equal delta. And that ends the proof. Okay. So as you can see, we have obtained two useful estimates here. If we go back to the previous, to the full lemma, here we have two stability estimates. One is in terms of the stability error, where we describe the error between the approximates using the exact case and the noisy case. And in the second one, we have the stability estimates in terms of the residuals. And now we will use them in the next lemma, which is our first convergence estimate with the discrepancy principle. So that's lemma 3.20. With the same condition on the step size eta, it follows that the n sub delta is finite. That means our discrepancy principle is well defined. And also we have that very helpful limit there. And note why that result makes sense is because if you look at the limit there, note this must be treated accordingly because note this n delta, the choice of n sub delta depends on delta, but note it's not explicitly expressed there. But we have this very useful result, which should be useful later on. So to prove that one, let's first solve that n sub delta is finite, and the proof requires the previous results. Okay, so again we use the same decomposition as what we have on the residual. Okay, and it's like this. So for maybe I'll just okay. Say for n from 0 to less than n delta. Okay, but before that, let's try to rewrite this very nice composition. Actually, something that what we had last time. So that's axn. That's actually x sub n delta minus y delta minus. So we write ax n minus y in this in terms of these very useful terms. You have a sub x n delta minus y delta minus ax n delta minus a x n minus y delta plus y. And why we want to do that? Because we want to use the previous the estimate from the previous results. Okay. Now, if you look at this one, this is just difference of two terms, and then by triangle inequality, you can write that a sub xn minus y, the norm, is less than equal to the difference of the two norms. Okay, so that's equal to norm of ax n delta minus this one. And I'll first factor out a over here. Okay, and how does that work? It's from a version of triangle inequality, which actually looks like this. So it's like if you have, let's say, the norm of P, how do I say this? Or maybe Q, or maybe let's just say like Q. Okay, and then less than equal to norm of P minus Q plus norm of Q. So by using this term over here, then you can actually apply this result. So P minus Q is actually this one over here. So that's P minus Q. Okay, so that's P and Q. Okay, so I hope that's clear. And then from this one, we'll use the discrepancy principle. Okay, now because we take n to be less than delta, so that means n here is doesn't satisfy yet the discrepancy principle. So therefore, this first term here is still less than equal, actually less than tau delta. That's fine over there because we have less than equal here. And by the previous lemma, lemma 3.19, the one we just proved, this is less than equal to minus delta. Okay? In particular, this is equal to tau minus 1 times delta. Okay? And then, now we can use that bound over there in showing that n delta is finite. So it's like this. So by using that one here, then we have something like, let's see, let me just write that one, T tau minus 1 delta less than equal to norm of. And then we can take the sum from n equals 0 to n delta minus 1. So we'll have something like this. The summation of, now let me just use J. The square here. So square, square, square. And then from this one, we take J from 0 to n delta minus 1. So be less than equal to this one, tau minus 1 square times delta square times the number of terms in the summation. In this case, that's just n sub delta. And from lemma 3.17, we know this sum is just bounded above by 1 over C sub O times square. Notice this is finite sum, so it's bounded. So notice this is finite sum, so it's bounded above by the infinite sum, which is what you see in that lemma. Okay, and then from this lemma, or rather from this inequality, we can see that n delta is finite. Why is that? Because we can write n sub delta in this way, which is square. Notice this is these are all given constants there. There's no term there in terms of an iteration number, so it's finite. So that means n delta is finite. Okay. What time is it? Okay. Now you can finally show the desired limit result. This one. Now, first, note that we need to consider two scenarios here. Note that the regularization parameter given by n sub delta could converge to either finite, or it could converge to a finite number, or it could converge to an infinite number. Okay. So now what we will do is we'll just consider assume the case that let's just assume that the regularization parameter goes to infinity as delta goes to 0. The assumption that n delta approaches to a finite number can be proven actually much simpler than this one, though it just uses the same results. So what we'll do there is this. First, we let n hat delta be the smallest integer greater than or equal to n delta over 2, which is a well-defined choice of n hat delta by the assumption over there. So the existence is guaranteed. Okay? And then by the same result here, by using the same result here, okay, and if you do that again, but by summing up from j equals n hat delta to n delta minus 1 of this one, and then of course this is similarly, this is bounded above by this one, tau minus 1 square delta square times n delta minus n hat delta. Okay, hope that's clear. Okay, and then from that we can also show this result using lemma 3.17. Note by lemma 3.17, this implies that this thing here, in fact, the entire summation goes to 0 as delta goes to 0. Okay? And note by our choice of n hat delta there, note n hat delta is less than or equal to n sub delta over 2 plus 1, right? That's by definition of n hat delta, because it's the smallest integer greater than or equal to n hat over 2. So therefore, n hat delta is less than or equal to that n sub delta divided by 2 plus an integer. In this case, we just use plus 1. And also, by definition, we can see that n sub delta minus n hat delta is less than or equal to n delta minus n delta over 2 plus 1. Which is just equal to n sub delta over 2 minus 1. Okay, so therefore, what you can do is by using that last summation there, we can in that expression that we just wrote in terms of the summation, we can use it with the useful lower bound, which is equal to that one that we just wrote over there. Then it follows that then it follows that tau minus 1 square delta square times, that should be n sub delta, how's that again? Minus 1. This one is less than or equal to that same summation, which goes to 0 as delta goes to 0. Or in other words, but before that, we can also write it in a much clearer way, okay? Because this will imply that tau minus 1 square times 1/2 times n sub delta times delta square is less than or equal to tau minus 1 square times delta square. Yep, plus that summation there. Now, of course, this goes to 0 as delta goes to 0. And from lemma 3.17, this goes to 0 as delta goes to 0. So that means this one here, in fact, we can ignore the constants, this one. N sub delta times delta square goes to 0. And equivalently, this means that the corresponding square root goes to 0. So that means it also follows that n sub delta to 1/2 times delta goes to 0. And that finishes the proof of this useful result. This result will be useful in proving our convergence result for the Landweber iteration by the discrepancy principle. And that is given by Theorem 3.21. Same if our eta is chosen appropriately, and if you let n delta be the integer determined by the discrepancy principle with tau greater than 1, then the limit of the errors, which is the error between the regularized solution and the exact solution, must go to 0 as the noise goes to 0. Okay. And to prove that one, we'll use the previous lemmas that we have. So it's a very short proof, actually. So here's how it works. Let's prove for the first one. For the first case, let's assume that, same as we did earlier, we assume that n sub delta goes to infinity as delta goes to infinity. So in the first case, it's actually green. Let me get a white one. Okay. So here, and then we use lemma 3.19 over there, which there's actually a typo over there. I will correct it later on. Now, by triangle inequality, note that we can decompose x sub n delta, the error between the regularized solution and x dagger, in this way. Note this one is for the exact data case where we terminate by the discrepancy principle, plus this one. And then by triangle inequality, you have this one. Okay, and then from lemma 3.19, we can bound the first term here. Is it or rather 3.19? Yeah, yes, it's 3.19. The first term here can be bounded by C1 times n sub delta raised to 1/2 times delta. And look, this term here is familiar, right? And then plus the same here. Okay, and then from the lemma we just finished proving, we know that as delta goes to 0, this one goes to 0 as delta goes to 0. For the second term, n sub delta goes to infinity, and by lemma 3.18, we know that this converges as delta goes to 0, because as delta goes to 0, n sub delta goes to infinity. Okay? So that means for the entire term, this means that the regularized solution, the regularized solution the error between the regularized solution and the exact solution goes to 0. Okay? There. Okay, so that's how it works for the first case. For the second case, we use the discrepancy principle. So for case 2, we assume that this time n sub delta converges to a finite number or integer. Okay, and then we may assume that when delta gets small and delta, the regularization parameter equals already that finite number for some small noise level. Okay. Now that means by discrepancy principle, using discrepancy principle with n sub delta equals n sub O, that means that A sub x sub n O minus y delta is less than or equal to tau delta. And also from the previous lemma, lemma 3.20, we can also compute the error that x sub n sub O delta is x sub n O is less than or equal to that term over there times delta. Okay. And then what will happen is this. Now, if we look at the, I'll just write it here. Notice one, as delta goes to 0, we know that this one here goes to 0 as delta goes to 0. So therefore, this one goes to 0. So that means I'll just write it here. So that means x sub n sub O delta converges to x sub n O. And also, for the discrepancy principle, this one goes to 0 as delta goes to 0. So therefore, this one here also goes to, it must also decay to 0. So that means that and from that one, as delta goes to 0, we can also show that norm of A sub x n O minus y delta goes to 0 as delta goes to 0. But that simply mean that we have the following result. Note this one, this simply tells us that A sub x sub n O delta approaches A times X sub NO by continuity of A, of course. And also, it also follows that A sub X sub NO from this result over here, okay, this also implies A sub X sub NO goes to, of course, you have Y delta there. Of course, it must approach to Y N sub O, yeah, N sub O delta, yeah, A sub X sub NO. Wait, did I put some? Oh, sorry, there should be delta there. That's why I get lost. Okay. Yes, this one. Okay, and then of course that means that A sub X sub NO delta approaches Y as Y delta goes to 0. Now you have these two sequences here that converges, then they must converge to the same limit. Therefore, A sub X sub NO equals Y. And by following the same argument here, it follows that the X sub A, the solution at X sub NO satisfies our linear problem. Okay, and now it also follows that by using that fact, let me just continue it here. Okay. Now, what does this result mean? That X sub NO solves AX equals a linear problem, AX equals Y, and it can also be shown that by definition of Xn, you can check that X sub n is equal to X sub NO for all n greater than equal to this N sub O, which is the finite number where our regularization parameter works. Now, how is this true? It's like this. Let's say if X sub NO plus 1 by the Landweber iteration, O minus eta times A star times A sub X sub NO minus Y. Since X sub NO solves AX equals Y, this is 0, so you're left with X sub NO. And by that, the same argument, this thing follows. Okay? So that means that in the Landweber iteration, by the discrepancy principle, the solution doesn't change when we go beyond N sub O iterations. All right? And also by theorem 3.18, okay, we know that X sub n goes to X dagger as n goes to infinity, right? And note these two results here. You see, note this tells us that X sub n sub O must be equal to X dagger. Why? Because here this is just equal to saying that if n goes to infinity, then it will just, this is like the limit as n goes to infinity. So that means X sub n sub O is just X dagger. And that actually proves the result. That means the regularized solution, X sub n delta, minus x dagger approaches the, where was that result again? This one approaches x sub no minus x sub no, which is 0. And that finishes the proof of the convergence of the Landweber iteration by the discrepancy principle. Okay? So that's one result. So we know that it converges. And aside from the converges in Hilbert spaces, it also allows us to describe the rate of convergence. And that is related to the result on the convergence rate of the method. And same as in the Tikhonov regularization, we need a smoothness condition, which is this one, which is similar to what we derive for Tikhonov regularization. Okay, but because it's already 4 p.m., so we will continue discussing this tomorrow. And then, since I think we'll have some time, we have a lot of time, I think we can add more topics on this one. Okay, still under still like an introductory topic on inverse problems. So that's it. We'll continue next time, which is tomorrow. So thank you and see you.